Hey everyone, today there's something a bit different. I just competed in the CODECHEF Div2 contest, and as of right now I'm actually winning with a score of 600. It's possible, but I doubt that anyone's going to overtake me at this point. So I did miss one problem, but I thought I'd go through the rest of the problems, and this includes the the Division 3 problem. So let's start with the division, I think is the Division 3 problem. Alright, so this is just an implementation problem. Simply for each test case we do exactly what the question says. We read in 3 pairs of integers, and then we just output the maximum sum out of those pairs. So here's my code. I just read in the 3 pairs and then we output the maximum. There's not much for this problem, so I'll just move on. Then we have this problem, which also doesn't have a lot going on. So we need to fill the grid such that the bitwise XOR of the rows, columns, and diagonals are all equal. The other thing to notice is that the grid is size n by n, which means that the rows, columns, and diagonals all have size n, and that means that an easy construction is just to make sure that each row, column, and diagonal contains the same n integers, because that means that the bitwise XOR will also be the same. And of course, the easiest solution is just to print out a grid of 1s, because that means that each row, column, and diagonal will just have n 1s, so they'll have the same bitwise XOR. Not much else for that one. And also, I think for this problem I didn't like especially. To me this was a sort of, it was just a small case bash problem, and I didn't find it particularly interesting. But anyway, I'll go through my solution. The key thing to note is so how does bitwise AND work? Bitwise AND works is if we take a bunch of integers and we line them up and we align the digits, then for the bitwise AND, we will have a 1 set in a position if and only if all of the numbers contains that bit set. So for my example here, the AND would be 0, 0, 1, 0, 0. And what this tells us is we notice that whether an integer is odd or even depends purely on the least significant bit, or this bit. If this bit is a 0, then it's even. Otherwise, if it's 1, it's odd. So, what if we know that, say that the bitwise, let's say that the 1 of the answer, let's say that the least, how do I put this? Let's say that we know that the bitwise AND for all these numbers is odd. That means that it contains this last bit set. That means that we know that each of these n numbers must also contain this bit set. We know this rightmost column for sure, and because this number will be odd, this number will be odd, this number will be odd, and we know that this n integers, we can determine if the sum is odd or even. So if n is even, then an even number of odd numbers added together will be even, and if you take an odd number of odd numbers and you add them together, you'll get an odd number, and that explains this case. The only other case is if n equals 1, then clearly the bitwise AND is just equal to the number itself. So we can determine that the only element must indeed be A, so we can just directly check if that's odd or even. And then finally, in all other cases, it's impossible to tell. It's impossible to tell, and that's because the only other case is when n is greater than 1, and it does not contain this, and the bitwise AND does not contain this bits set. And in that case, we can definitely provide. Okay, we should also I can also mention that we can just ignore the other bits. Only the least significant bit actually matters towards the bitwise AND, so we can pretty much just we can consider this only by the last bit. And since n is greater than 1, we can make two constructions. We can have one construction where one element has the bit set, i.e. one element is odd and the rest is even, or we can have a construction where all of the numbers is even. And one of these constructions is guaranteed to have an odd sum and the other is guaranteed to have an even sum. And therefore that shows that it's impossible to tell what the parity of the sum is, because we found two constructions with different sum parities. And that's all for that problem. Next, we'll go for this problem, if I remember what it is. Okay, so at first glance, so the most important thing is to understand what this operation really means. So we're taking the lowest index, and then m minus 1 times we go to the person with the next highest index, and then finally we take that person and we remove them. And the key observation is that all this does is this removes the person with the nth lowest index. So we start with all n numbers from 1 to n, and then n minus 1 times we will take out the nth lowest number. So for example, if n is 6, then we have 1, 2, 3, 4, 5, and 6 in the list, and then if m equals 3, that means we're just getting rid of this 3. And that's pretty simple. The only other case is, what if m is greater than n, then the nth number doesn't exist. But here we'll just use, we know that it's going to keep wrapping around the array since it's circular, so we can just take 10 mod 6, which is 4, and then we know that the fourth person is the one that's going to be eliminated. And okay, so once we figured out who's the first person to be eliminated, then what do we do? So let's say we start with 6 people, and then I removed this 4 because m is 10. Now, how am I going to determine who the last person is? Well, I don't actually know I haven't actually worked out the specific answer of this test case, but let's say that, for example, let's say that when we had 5 people, the answer was 2. Then we know that once we've done the operation of removing 4, we've just reduced the problem to having n equals 5 and still have m equals 10. So if we know that the answer for n equals 5 and m equals 10 was 2, then we know that the answer for n equals 6 and m equals 10 is also equal to 2. But let's say that the answer for n equals 5 was instead 4, i.e. it was the fourth largest element. Like, pretend that the answer for this is 4. Then we know that once we've taken out this 4, then the winner will be this one, which is actually 5. Since we've taken out an element that's lower, we've kind of bumped the indexes of these people up. But we know that the fourth smallest person in the resulting list is going to be the winner if we already knew that the answer for n equals 5 and m equals 10 was 4. And that means that assuming m is fixed, we know that if the answer for n minus 1 people is less than the person we removed, then the answer equals then our current answer is simply equal to the previous answer. And otherwise, our current answer is equal to the previous answer plus 1, because we have to remove this fourth person, and that reduces us to the other case. But since we removed a person below, we have to make sure to add 1 back so that we get the original numbering scheme. And that's since answer only depends on the previous answer, that means we can just do dynamic programming. This is pretty simple dynamic program because it only has ON states and it has a very simple O1 transition. So that means that the overall time complexity will just be ON per test case, which is good. So I'll just quickly show my implementation. In my implementation, here y is the person who's being removed, you may notice that I subtract 1, take the modulus, and add 1. That's just a quick trick, because if, for example, if m was 12 for n equals 6, then 12 mod 6 would be 0, but we don't have a person numbered 0. So instead the -1 take the mod +1 trick will, instead of doing 0, it will just give us 6. It will, if you do like a -1 mod m +1, that will do like, this is like modulo m, but in the but it will output a number between 1 and m instead of 0 and m -1. So that's just a quick implementation tip. And then finally, we do exactly what I put here. I just implemented this. I won't go over it again. And then there's just outputting the answers. Alright, that's it for that problem. Now for the next problem. Okay. So in this problem, okay, let me try drawing an example tree. I'm pretty bad at drawing with my pen, but let's just look at. I think the example tree was something like this. And let's just give a concrete value. Let's just say that, for example, we are asked what in 10 seconds how many drops hit root 1. That's 10 seconds with terrible handwriting. I'm so sorry about that. And basically, instead of seeing how many raindrops hit the root, another way to see this is for each leaf, how many raindrops which landed there will make it to the root. And for example, we can see that a raindrop, if it landed on 2, it would take 1 step to hit the root. And that means that we could get 10 drops for this, 10 drops from this 2 would be able to make it in the 10 seconds. Whereas, for example, this 4, a raindrop would take 2 seconds to make it to the root. And that means that we can't have all 10 raindrops make it, but we can only have 9 raindrops make it. And you should be able to see that the number of raindrops that make it from a root node is equal to okay, the time, I don't know how to draw with my mouse, I'm so sorry. The time minus this is because I'm on my laptop, oh no. Minus the depth plus 1. Okay, I just failed at handwriting, but that's the main idea. The other idea is that we only care about what happens after the nth shake, which means that we can process everything offline. And also, it's also like interesting to mention that if a leaf node was like 15 away from the root, then none of the raindrops would make it to the root. So we can't have a negative contribution. I'm just going to go back, so I can. How do I type again? Okay, this is kind of annoying. I guess I'll type here. So if a node is depth x away from the root, then time minus depth x plus 1 raindrops will make it. And because this plus 1 is just kind of annoying, let's just move the plus 1 over here. And that means that basically we can just increment time to start with, and then it's just time minus depth x, which is easier to implement. And so for each time, and by time I mean time between shakes, or like time from the beginning to A1, or the time between A1 and A2, and so on. That's what I mean by time. That's the time when drops are able to make it to the root. Anyway, for each time, if we have the depths if the depths of the leaves are, let's say, A1, A2, A3, up to AK, and we have a time of t, when I say t, this t is going to represent, it's actually going to be time plus 1. But I'm just incorporating the plus 1 beforehand, so it's a little bit easier to deal with. Then the number of raindrops from the first leaf will be the maximum of 0 and t minus a1. And then the contribution of the second one will be max of 0 and t minus a2. And you can see this keeps going. But unfortunately, summing maxes of 0 stuff, that's actually quite hard to do efficiently if you ever want to do many queries. So instead, what if I said, let's, instead of processing all leaves, let's only process the leaves, process the leaves which already are greater than t. We're only considering leaves which are already close enough to the root for drops to actually make it. Then the number of drops that make it is just this, t minus a1 plus t minus a2 plus t minus ax. And we should be able to see that this rearranges to be t times x minus the sum of a1 up to x. And this is the formula that we want. And the last thing, or one of the last things to consider is, well, we can't explicitly find the leaves that are close enough each time. But instead, if we sort the list at the beginning, let's say we sort the list of depths of each leaf at the beginning, then the set of nodes, sorry, this should be ai less than or equal to t, then the set of nodes, the set of leaves which are able to contribute to the answer, that will form a prefix of this sorted list. And that means we can just binary search to find the number of elements which is less than or equal to t. And then to pre-compute this sum, we can just use prefix sums. So I'll quickly run through my implementation of this problem. Okay. What exactly am I doing here? Okay, so at this point I'm just reading in my edges. I'm doing a DFS to get the depths of each one. The depths of each leaf. And then here in my code, Beth is like the previous time that Beth is either the previous time that the tree was shook, or 0. And that means that Beth minus the current time we're reading is the amount of time that the drops have to make it to the root. Oh, actually, I believe binary search is one possible way of doing this problem. In fact, I think there is another way of doing this problem, where instead we'll define an array b1, b2, b3, and so on up to bn, where bi equals to the number of leaves which are at distance I to the root. And now we don't even have to binary search for the elements that are less than or equal to t. We know that the ones that can make it is just b1 all the way up to bt. And then all we need to do is, so this b array, instead of being the sorted list of all the leaves, of all the distances from the leaf to the root, this is now actually a frequency array. So b1 is the number of leaves which are at distance 1 from the root. And that means that we have a slightly different formula, I believe. And that is what exactly am I doing? Well, it's not strictly up to bt, it's up to b of min, t, and n, because if t is really huge, we don't want to create a really long array of b, so we'll just make b up to length n, and then we'll just do b, and then we'll only consider index distances up to n, because it's not going to exceed n. It's actually going to be strictly less than n. And then what exactly am I doing? Okay, here's what I think I'm doing. Okay, if we consider leaves at distance I from the root, there are bi of them, and how many of them will be able to okay, how many of them will be able to make it to the root? Times p. Well, it's t minus 1 like times bi will be able to make it to the root. Okay, and then so if I sum this up over all t, this is going to be t minus, this will be like t minus 1 by b1 plus t minus 2 by b2 plus t minus 3 by b3, and so on. And if I expand this, you can see that this is just t times b1 up to bt, subtract b1 plus 2 times b2 plus 3 times b3, like this. So this this can be expanded and rearranged to give this. And then I simply maintain these two prefix sums, and that corresponds to PSA and PSA2. So PSA in my implementation corresponds to this prefix sum, and PSA2 corresponds to this prefix sum. And yeah, that's basically my solution. Okay, I'll move on to the next problem. I wonder if I'm still rank 1. Yep, looking good. Okay, so this is a slightly... This problem actually gave me way... I don't know, I actually struggled with this one a little bit, just because I wasn't thinking quite properly. Oh wow, I'm the only solve for this one. Maybe I should have gone to try that problem. Oh well, we'll just ignore it. So this problem at first it looks quite daunting. This problem, because n can be up to 2 to the 59, which is huge. But the thing to notice is, since this is a perfect binary tree, that means that each node basically each node in a particular level of the tree, or at a particular depth of the tree, can be treated identically. It will have the same number of values for everything, because everything is symmetrical. And that's the key idea of this problem. The main idea is that we can consider, for example, how many ways are there for for a tree with height h and the value of the node is x. Let's just say it doesn't define what's an... Oh, it actually does, but strictly less and strictly more, basically everything is interchangeable, because if I say that how many basically the ways for like less and more are both interchangeable. So I'm actually going to slightly change the definition of like a good tree, and I'm going to say how many ways are there for a tree with height h and the value of the node is x, and the children of the root are less than the root's value. We're going to zigzag like if 8 is the root of the tree, for example, then the children could be 4 and 6, and then the next level might be like 5, 7, 7, 8, or something like this. This is slightly different to their definition, so in their definition the children of the root are actually more, but we'll see that it doesn't actually matter, and that's because everything is symmetrical. So if I instead replaced every node with value, if every node in the tree currently had value vi, and then I simply replaced each node's value with m minus vi plus 1, then every condition would still be the same. Every node would still be in the range 1 to m, and the alternating condition of the tree would still be the same, and the only difference is that that the first level would be that the root would be greater than the children, whereas before the root would have been less than the children. So we can see that whether the children is less than or greater than the root, it's irrelevant as long as we maintain this condition, this alternating condition. So I'm just going to define it as the number of ways for the children to be less than the root's value. Okay, and since this is I think it's a pretty obvious example of an instance where you would apply DP, mainly because we don't want to calculate these states for every node. There's going to be a lot of symmetry, and it's pretty clear that the number of ways for a tree of height h is going to somehow relate to the number of ways for a tree of height h minus 1. Okay, so let's say that the root of the tree is x. Then the children of this tree can be y and z, and we need x to be greater than y and z. That's some beautiful ASCII art for you there. That's my tree. And then, okay, let's just focus on the left child, because the left child is totally independent of the right child right now. And basically, y can take the... Why is my caps lock on? Y can take the values from 1 up to x minus 1. And if y takes the value... Okay, if I assign y value, then the number of ways for left tree equals to the number of trees with height h minus 1, the value of node is y, and the children of the root is greater than the root's value. But because this is DP, we want our child state to mimic the original state, so we can do DP recurrences. And this is where the idea I mentioned before of less than or greater whether the children are less than or greater than the root is interchangeable, as long as we replace all the values v, and we replace all values v to m minus v plus 1. So in fact, rather than the value of the node is y and the children of the root is greater than the root's value, we can instead replace this greater with a less than, and replace this y with m minus 1 y plus 1. And that's it for the left child, and the right child will be exactly the same. Therefore, if we find the number of values for I'll just write this recurrence explicitly. The number of ways for a tree of height h and a value of x is equal to the sum of the number of ways of a tree of h minus 1, and this value can go from anywhere from I believe it's from m minus x plus 2 up to m. That might be off by no, I think that's correct. This may or may not be off by 1, but I think this is correct. If you take every integer in this range, this is an inclusive range, and you summed them up with this DP, then this is the number of expressions, this is the number of ways for the left child for the left subtree to be done. And then the right subtree will be exactly the same as y, and it's independent, so I can just take this number and square that. And that gives us an O height times m squared dp solution, because calculating this sum, naively looping through it, that will take om time, and there's also oh times m transitions. So that's not going to pass, that's too many operations. So how can we optimize this a little bit? Well, the thing to notice is that since this is a sum of a contiguous range, then once we've calculated the dp values for dph minus 1, we can just create a prefix sum out of those values, and then we can calculate this sum in O1 time, and that's going to reduce our complexity to O height times m per test case, which is sufficient. So, okay, the contest is nearly ending. I hope that doesn't mess with anything. I'm just going to quickly show my solution here. So I'm not going to really go through my code, but in my code I'm doing rather than doing all the dp values and then building a prefix sum on top, I'm simply doing that in one step. So in my definition here, dpij is the number of ways for a tree with height I, and the value of the node is j or more. So the j or more, the or more part is already incorporating the prefix sum parts. And I won't really go through the code, but basically this part just finds h, which is the height of the tree. This is some base cases, and this dp I minus 1 times m minus j plus 2, because of how I've built my dp table, this actually is the prefix sum for the previous row. Then I just square that, I add on dpij plus 1 for the prefix sum, then I just output the answer. Okay, so since contest is over, I can check, and someone actually did solve another problem. They solved the other problem than me, but I have won this contest. So this is my second. Actually, the last contest on this count was also a first place Div2 contest, I think. So that's pretty good. And then finally, this problem. I think I was the. Did it say that I was the only successful submission in Div2? I know that there was Div1 solves. Yeah, so I was the only solve for this problem, so that's pretty cool actually. Anyway, I'll go through how I solved it. My solve is a bit unconventional, but basically the problem says, out of all the integers from 1 to m, how many of those integers contain all the prime factors belonging in a set S? And the immediate thing to notice is that the size of the set is really small, so that's less than 20, which for me it hints at some sort of exponential solution. The fact that it has distinct prime numbers it doesn't matter that much. If it didn't have distinct prime numbers, we could just make them distinct and remove duplicates. But anyway, so basically, this is what a simple backtracking solution works. Because in my mind, if I see n equals to 20, and I know intuitively, I know that the number of answers, it can still be really big, but it's not going to be ridiculously huge. It's not going to be like 10 to the 100,000 or whatever. It's going to be fairly, like, in the grand scheme of things, it's going to be fairly small. And we know that it has to fit inside the length of a long anyway, because so it's not going to be that bad. So anyway, here's my backtracking, a simple backtracking solution. Okay, let's just take away some of these stuff for now. Let's ignore the parameter up for now. Basically, up is like the last position after we've checked. So if we need to check the primes from S0 up to S5, then what we can do in our backtracking solution is, if we try to check the prime S6, which doesn't exist, that means that we've finished our backtracking. We've reached like a leaf state, and in that case we'll just append V to the vector of numbers that we can make. So v is the current number that we've made, x is just a vector of all numbers that we've made so far, and current is which prime in S we are considering right now. And then otherwise, either we don't take any prime, either we don't take another prime, we don't take S current as a prime factor of v, in which case we just backtrack to the next prime, or we will backtrack to this state, which is we took this current prime factor, but I'm using current here because we could take this prime factor multiple times. And just a quick tip here, when we want to check if v times s current is less than or equal to m, this can overflow a long, and you could use like int 128, like a 128-bit integer, but instead I will just rearrange this to use division, and even though division is a bit slower than multiplication, this will ensure that our stuff doesn't overflow. So that's my backtracking part. So I just created this backtracking bit, and in CP helper I just created my own test case for 10 primes. So if I choose the 10 lowest primes, this is going to be the worst case because this is going to have the most valid combinations, and then I chose the max m. And I noticed that what was it? I can't remember. For this, for only 10 primes, in the very worst case, I only generated about 13 million distinct answers. And that means that if I do 20 things, I can expect it to be, like, at the very worst case, this squared. So 13 million squared, that's still like 200 trillion or whatever, 169 trillion. That's way too big. Obviously we can't backtrack that. But since we have two parts combining, basically if we separate our primes into one set, set A and set B, and we run our backtracking on both set A and set B, then any number in the final output that we should be considering is we can split that number into two factors, where one factor consists of the number made out of one factor consists of the numbers only containing the lower set of factors, and the other side considers only the right hand side of factors. Like, that might not make so much sense. So I'll give an example. Let's say if n equals to 4, then on our left hand side we could, for example, if we only consider the 2 and 3 as set A of our primes, we could make the numbers 1, 2, 3, 6, like 1, 2, 3, 4, 6, 9, 12, etc. And then if we consider our right hand numbers, we can make like 1, 5, 7, 25, 35, and so on. And now, for any number that can be made out of these full set, for example, 42, I can break this 42 into two factors, 6 and 7, such that this 6 is found in the first set and this 7 is found in the second set. And that's just, we just split 42's prime factors. Like, the reasoning why this works is 42 equals 2 times 3 times 7, and then out of these factors, if we consider like the product of the factors of 42, which is part of the lower set, 2, 3, that will give us the first factor in L, and then the remaining numbers will give us the other factor. And this idea that any number can be split across these two sets, that's quite important. I.e., if you generate these backtracking sets, and then if we were to take the pairwise product, if we were to loop through all pairs of elements in L and match them with pairs of elements in R, and we took the product of all of those, and we chucked everything into a set, the size of that set, which is the number of elements in that set, which is less than or equal to m, would be our answer. And this technique, by the way, is called meet in the middle. That's when you split something into two different sets. You usually run some sort of exponential solution to them, and then you combine them at the end. This is called meet in the middle. Now let's give another concrete example. Let's say n was equal to, let's say m here, m was equal to 50. Then I don't want to loop through all pairwise products, because that's just going to give me the 169 trillion combinations. I can't afford to do that. And instead, what we notice is that, for example, this 2 will be able to form products with this prefix of r, and this 3 will be able to form products with this prefix of r, and because assuming L and R are sorted, of course. And that means that once we've found L and R, we can simply sort R, and then for each element in L, we just binary search to find the prefix, the number of elements in R, such that the product of our current element L and the largest and the number in R is less than or equal to m. I.e., for each element in A, we need to find the largest B in the largest B such that A times RB is less than or equal to m. And we can rearrange this a little bit to give RB is less than or equal to m divided by A, and that, again, that avoids overflow or the use of int 128. And that just means that all we have to do is, for each element in L, we simply add to our answers the number, we simply find the largest B such that RB is less than or equal to m divided by A, and then we add B to our answer. And in my code, okay, this is my actual code, so I won't bother getting it up. This is useless. This is just a small brute force thing I use to validate my solution. Basically, I'm backtracking twice, once for set A and set B. And now you see what the point of the variable up is. Up basically specifies the range of the primes we are looping up to. I.e., for set A, we should only loop up to half of the primes, and then for part B, we should start at the halfway mark of the primes and loop up to all of the primes. And that means that I can just easily generate, or we can do the backtracking for sets A and sets B. And then once I've sorted B, for each element in A, I'm just using upper bound because it's a fast, easy binary search, and then I print out my answer. It's also worth noting that I think you can, if you sort L and you sort R, then you could do a 2 pointers approach, because as you move L up, the length of the prefix in R can only ever decrease. But you're sorting L and you're sorting R anyway, so you're still going to get a log complexity whichever way. So I find just binary searching is easier. Anyway, that's all I have for this video. I'm pretty happy with this how this went, despite not AKing this set. But let me know if you want to see more CODECHEF or similar contents in the future, and see you then.